In this section, we'll go into more detail on how OFDMA creates a more efficient payload delivery system. OFDMA uses 4G LTE's proven and foundational OFDMA technology for efficient access. It allows multiple users with varying bandwidth needs to be served simultaneously. 802.11a up to 802.11ac use OFDM, or orthogonal frequency division multiplexing, to deliver Wi-Fi data packets. Under OFDM, a device uses a fixed 20, 40, or 80 MHz of bandwidth to deliver the packets regardless of whether it's transmitting video or just sending a simple text message over a Wi-Fi network. We'll use a simple analogy using trucks to illustrate the difference between OFDM and OFDMA. For OFDM, each truck is hauling a payload or user data, one surfing the web, another uploading video from a soccer game, and a third sending a text message. This is like using 3 trucks of the same size to send the data regardless of how empty or full each truck is. In other words, OFDM inefficiently uses the bandwidth, leaving a lot of empty space. 802.11ax, however, uses OFDMA, or orthogonal frequency division multiple access, which allows resource units, abbreviated RUs, composed of a certain number of subcarriers or tones that divide the bandwidth according to the needs of the client and provides multiple individuals the same user experience at faster speeds. In our truck example, OFDMA allows a device to fill an entire truck with resource units, a payload delivery model that uses the bandwidth much more efficiently. Let's go into more detail on exactly how this is done using 11ax. We'll start by defining some terms and concepts. Multi-user, or MU, applies to multiple technologies in 11ax, so it's important to understand that the term multi-user does not reference a specific technology, such as multi-user MIMO. It means that transmissions between an AP and multiple Wi-Fi clients can occur simultaneously depending on the supported technology. 11ax defines the use of multi-user orthogonal frequency division multiple access, abbreviated MU-OFDMA, and multiple use, multiple input, multiple output MU-MIMO technologies. OFDMA is a multi-user version of OFDM in that it allows multiple users to share the available bandwidth and transmit simultaneously. A single user gets the entire bandwidth at any given time regardless of the packet size. For a text message, this is like putting a small box in a big truck. Each AP can speak with only one device at a time. As such, they are client-centric with a randomized contention-based approach that regulates Wi-Fi to a free-to-send, first-come, first-served paradigm, which is untenable for modern high-density and large-scale deployments today. Multiple users are separated in the time domain only. In our example, we have user 1, 2, and 3. User 1 is transmitted first using the entire bandwidth, followed by user 2 and then user 3. In contrast, OFDMA is AP-centric. It enables 11ax AP to simultaneously communicate with multiple devices by dividing each Wi-Fi channel into smaller sub-channels known as resource units, or RUs, or sometimes called RU tones. The minimum size of one RU is 26 tones or subcarriers, which equals approximately 2 MHz. A 20 MHz channel can serve up to 9 users. The access point determines how to allocate the sub-channels, as each individual RU can be utilized for different clients that are serviced simultaneously. In other words, an AP can choose to allocate the whole channel, all subcarriers within a channel, such as a 20 MHz channel, to a single user in a given time frame, or it may partition the whole channel to serve multiple devices simultaneously. This technique improves the usable throughput for all devices connected to an AP. This reduces the use of the contention methodology that preceded 11ax and moves Wi-Fi from a contention-based to a schedule-based service, which is analogous to an unmanaged four-way street intersection finally getting a traffic light. This helps stabilize Wi-Fi performance, especially in higher density environments such as stadiums, convention centers, transportation hubs, and auditoriums. OFDMA is most useful when multiple connections transmit limited amounts of data, which allows the protocol to squeeze smaller data packets through multiple sub-channels or resource units. Think of a delivery truck that can only send a package to one house at a time prior to 11ax versus that same truck able to carry multiple packages to multiple houses, which is 11ax. Moreover, OFDMA is effective at all ranges, close, medium, and far, and can help mitigate overlapping basic service set or OBSS interference issues. Let's look at how OFDMA subdivides a 20 MHz channel into smaller frequency allocations based on multi-user traffic needs. The AP decides how to allocate the channel, always assigning all available resource units on the downlink or uplink. By subdividing the channel, parallel transmissions of small frames to multiple clients can happen simultaneously. A 20 MHz OFDMA channel consists of a total of 256 subcarriers. These subcarriers, or tones, are grouped into smaller subchannels known as resource units, with a minimum size of 26 carriers, which will accommodate up to 9 users for every 20 MHz bandwidth. For example, when subdividing a 20 MHz channel, 11ax AP designates 26, 52, 106, and 242 subcarrier resource units, which equates roughly to 2, 4, 8, and 20 MHz channels, respectively. 11ax AP dictates how many RUs are used within a 20 MHz channel, and different combinations can be used. Here we show a 40 MHz channel. There are 512 available tones or subcarriers in a 40 MHz channel. One tone equals a single subcarrier of 78.125 kHz. For high bandwidth applications such as video, the AP can decide to allocate the entire channel to a single user. This would be the same as 11AC today and does not fit the definition of OFDMA. Or the AP may serve 2 users simultaneously, each occupying 242 tone resource units, each being approximately 20 MHz. For small packets such as IM or voice over Wi-Fi, the AP will mix and match different RUs based on traffic type. It can also divide up the resources all the way down to 26 tone RUs and in theory serve 18 users simultaneously. As you can see, OFDMA enables efficient use of available spectrum, especially for low bandwidth applications. Here we see the number of resource units or data tones available in an 80 MHz channel. We have up to 996 usable tones. This bandwidth can be used in dense user environments where many users would normally contend inefficiently for their turn to use the channel. This OFDMA mechanism now serves them simultaneously. This table shows the number of users that can now get frequency multiplex access when 11ax AP and stations coordinate for multi-user OFDMA operation using the 20, 40, 80, or 160 MHz spectrum. There are a few RU tones currently defined: 26, 52, 106, 242, 484, 996, and 2 times 996 tone RUs. The AP may allocate the whole channel to only one client at a time, or it may partition the channel to serve multiple clients simultaneously. For example, for basic 20 MHz bandwidth, 9 26-tone RUs can be used, meaning you can have up to 9 users, but only 4 users with 52-tone RUs. So let's put all this information together to show how OFDMA has a better packet delivery system. Here we're showing 2 technologies, OFDM and OFDMA. Let's say we take an 802.1140 or 80 MHz spectrum and break it into tones or subcarriers. For a 20 MHz channel, you would have 242 subcarriers or tones where the transmission takes place. For OFDM, all the subcarriers are assigned to one device, such as an iPhone client. Each frame is transmitted across the whole channel width. This is like one big 18-wheeler getting assigned to you without caring about whether you need to transport a small box or a large box. So for example, if it's a text message, there is a lot of unused space versus downloading a high-definition video. In this case, one size fits all. OFDMA gives the user flexibility. Frequency division multiple access is achieved by assigning different OFDMA subchannels to different users. In our 20 MHz channel example, the 242 tones are divided into smaller groups called resource units that can be assigned to different devices. This means each transmit opportunity can be shared across several frames, which means there is less contention overhead. For our example, client 1 gets 6 tones, which we'll call resource unit 1 for our example, although in reality a minimum resource unit contains 26 tones. Client 2 gets its own resource unit, and so forth for other clients. With OFDMA, I have the flexibility to assign different number of RUs to different clients depending on the type of data I'm sending. I can get everything to one client with the traditional OFDM way, or take some and give to different devices. In this example, we're splitting it into 6 chunks and giving it to 6 users. If I'm using it in the download direction, the AP could say that I'm going to use my first 26 tones or subcarriers, which is the smallest RU size, and transmit to client 1, and my next 26 tones transmit to client 2. This information will be provided first to all devices by a trigger frame, so they'll know that if I'm client 1, I look for what's coming in the first 26 tones. In my truck example, it's like the truck just picking up the first box, then the second, and so forth, becoming much more efficient than using 3 trucks. Here is another way of comparing OFDM transmission to OFDMA transmission efficiency. In this example, imagine an AP is talking to 20 clients. With OFDM, the first client, let's say an iPhone, gets allocated a chunk of data from the AP represented by the yellow portion of the frame on the upper left. After receiving it, it sends an acknowledgement back to the AP. Then the AP transmits data to the second client, which then sends its ACK back and so forth. The AP has to tell a whole bunch of other things to the receiver to make it work. This information is in the preamble portion represented by the red block. A typical preamble portion in a Wi-Fi packet is about 30 to 50 microseconds long, depending upon what you're doing. The yellow or data portion is about 10 to 20 microseconds. What I'm trying to highlight here is that I have a 30 to 40 microsecond preamble, which from the end user's perspective is useless information. This is followed by a 10 to 20 microseconds of real data, and then I have to wait for the acknowledgement back from the client and then start the process all over again. This means I'm using the medium in a very inefficient way, like 3 trips to carry 3 boxes in the truck analogy versus using 1 truck. I can avoid all this overhead by putting all the boxes together. If I'm serving 20 cell phone clients and I break my spectrum into 20 different audio chunks or resource units and pack them all together in 1 frame and send them to 20 different clients, this is much more efficient, which is what the bottom graph is showing. This reduces the medium usage and latency for short packets. Let's look at this short packet problem from the downlink perspective. I still need a preamble to tell the clients what modulation coding scheme, or MCS, I'm using, who has the data, that I'm packaging data for 20 clients, that the first box is for client 1, the second 10 boxes for client 2, and so forth. All this information is still in the preamble, but I'm assembling all the data together and sending it in 1 packet. It's also important to note that in 11ax, the preamble portion can be extended up to 3.2 microseconds from 0.4 or 0.8 microseconds in 11ac. We'll discuss this later. If I use the OFDM transmission method in the top diagram, I first talk to OFDM client 1, then client 2, all the way to client 20, and then come back to client 1. So client 1 sees a large latency from its perspective. If I use the OFDMA approach in the bottom graph, I can serve all those clients right away, so the latency comes down, which is a big deal. By using the OFDMA method, I have freed up a lot of airtime, so I have more bandwidth available to serve other users. If I have a mix of 11ax, 11ac, and even older 802.11 devices, which is how the world will look for quite a few years since all the devices are not going to go 11ax, then I will serve the 11ax devices more efficiently and free up the medium quicker, and then serve the 11ac devices. This allows more data throughput to serve the legacy clients. Let's look at it from the OFDM uplink point of view. In this example, 4 devices are trying to transmit data to an AP on an 80 MHz channel. In the traditional 11ac world, the way it would work is all 4 clients would compete for the medium. In this example, we'll assume that Station 2 wins. Station 2 transmits its data, and then the AP sends an acknowledgement back to Station 2. Then all the client devices do a random backoff, as that's the way the standard works. Then another device wins the medium, and in this example, Station 1 wins the medium, and then transmits the data and the AP acknowledges it. Then all the clients do a backoff. Then the third exchange starts, and let's say that there's a random backoff, and at this time 2 clients have the same random backoff parameter, which can happen in Wi-Fi today. In our example, both Station 3 and Station 4 say that they got the medium, and then there's a collision, and that time period is wasted. Both Station 3 and Station 4 don't realize that they've collided and wait for an acknowledgement to come back from the AP. After neither one receives an acknowledgement back, then both do a random backoff. Then Station 3 wins the medium, gets the acknowledgement back, and then Station 4 wins the medium and gets the acknowledgement back. In OFDMA, the uplink transmission is very different in that it is a scheduled-based transmission and the AP is in full control of the scheduling. This is done to maximize uplink transmission efficiency. First, the AP transmits a control frame called a trigger frame to all users, which contains scheduling information, including the resource unit allocation to be used by each station. The RU allocation information is communicated to the clients at both the PHY and MAC layers. The trigger frame also contains the number of spatial streams, the power control information, such that individual users can increase or reduce their transmitted power. In response to the trigger frame, multiple stations transmit simultaneously to the AP using a high-efficiency trigger frame format. To prevent interference, the packet's transmission from each of the stations must start and end at the same time, and they must remain synchronized in time, frequency, and power. Once the AP receives the packets from all the stations, the AP sends back an acknowledgement frame to finish the operation. You could say that the trigger frame is the master scheduler. So using our previous example, here is another view of looking at the OFDMA uplink process. With OFDMA, there is a concept called a trigger frame. This is what helps the AP schedule the uplink transmission. The AP says, I know that 4 clients are trying to talk to me, so I'm going to break this 80 megahertz channel into 4 chunks, give the first chunk to station 1, the second to station 2, and so forth, and transmit this information to the client devices through the trigger frame. In the trigger frame, the AP says that the green portion of this spectrum goes to station 1, and station 2, you use the blue portion, and so forth. All 4 devices talk at the same time, but they are using portions of the spectrum within that same 80 megahertz spectrum. Then the AP receives all of them together and sends an acknowledgement back. With one exchange, this whole process is complete without the individual clients contending for the medium, because everything is scheduled by the AP, and the AP is smart enough to recognize that it needs to allocate this spectrum for these 4 clients. This prevents backoff, as the AP sends the trigger frame and tells the clients that the trigger frame will end at a specific time. All clients wait for a short interframe spacing frame, SIF, which is about 9 milliseconds, and after that you guys transmit at the same time. It is a purely scheduled transmission. There is no one contending for the medium, and I freed up a lot of acknowledgement and random backoff and collision time by doing this. The question that's going to come up now is, how did the AP know that I have allocated the spectrum this way and these 4 clients have this data? I don't want to allocate spectrum to a client that doesn't have data. I'll explain this next.